Hello everybody, lesson 11, traverse surveys and computations. Meridians. Figure illustrates that geographic meridians is another term for a line of longitude. A line on the surface of the Earth joining the north and south poles is called a geographic, astronomic, or true meridian. The figure also illustrates that all geographic meridians converge at the pole. Great meridian is lines that are parallel to a great reference meridian, a central meridian. Rectangular coordinate grids are discussed future. And what is the magnetic meridians? Magnetic meridians are lines parallel to the direction taken by freely moving magnetized needles, as in a compass. Whereas geographic and great meridians are fixed, magnetic meridians can vary with time and location. This is equator and this is a central meridian. Geographic meridians can be established by tying into an exciting survey line whose geographic direction is known or whose direction can be established by observations on the Sun or on Polaris, the North Star, or through GPS surveys. A great meridian can be established by tying into an exciting survey line whose grand direction is known or whose direction can be established by tying into coordinate grid monuments whose rectangular coordinates are known. Meridians are important to the surveyor because they are used as a reference direction for surveys. All survey lines can be related to each other and to the real world by angles measured from meridians. These angles are called bearing and azimuth. So, about bearing. Bearing is the direction of a line given by the acute angle between the line and a meridian. The bearing angle, which can be measured clockwise or counterclockwise from the north or south end of a meridian, is always accompanied by the letters that describe the quadrant in which the line is located. So, for example, line located is quadrant north, line located in southeast quadrant, line located in southwest quadrant, and line located in northwest quadrant. So, for understanding the concept of bearing, the given angles for line K1 and K4 are acute angles measured from the meridians and as such are bearing angles. The given angles for line K2 and K3 are both measured from the east-west axis and therefore are not bearing angles. Here the given angles must be subtracted from 90 to determine the bearing angle. So, bearing angle for line K1, this is 21 degrees, 40 minutes east. K2, south, 71 degrees 30 minutes east. K3 10 minutes 38 minutes 10 degrees 38 minutes west from south, etc. All lines have two directions, forward and reverse. So here you can see illustration of reversed bearing. The directions are simply switched. For example, north to south and east to west. To illustrate, walking with a compass along a line in a northerly direction. If you were to stop and return along the same line to compass would indicate that you were walking in a southwesterly direction. When the meridian is drawn through point K, the line K1 is being considered and the bearing is northeast. If the meridian is drawn through point 1, however the line 1K is being considered and the bearing is southwest. In computations, the direction of a line depends on which end of the line the meridian is placed. So you can see, yes, line K1 bearing and line K1K bearing this one. Now about azimuth. Azimuth is the direction of a line given by an angle measured clockwise from the north end of a meridian. So K1 azimuth this one, K2 azimuth this angle, K3 azimuth this one, and K4 azimuth this angle, 334 degrees and 35 minutes. For example, the azimuth of K2 is therefore 90 degrees plus 18 degrees 46 minutes and total 108 degrees. K3 you can measure like 180 degrees plus 38 degrees. So azimuth of K3 will be 218 degrees. Normally, surveying problems are worked out by using either bearing or azimuth for the directions of survey lines. The surveyor must be prepared to convert readily from one system to the other. Here you can see illustration of relationships between bearing and azimuth. Here figure illustrates and defines the relationship, yes? So, for example, for northeast quadrant, bearing always equal azimuth. For southeast quadrant, bearing equal 180 minus azimuth. Southwest quadrant, bearing equal azimuth minus 180, and northwest quadrant, bearing equal 360 minus azimuth. We already know that a point can be located by polar tie, direction and distance, or by rectangular ties, two distances at 90 degrees. Here point B is located by polar ties from point A by direction, and N 71 degrees and distance 164 feet, 0.95. And point B on the figure B is located by a rectangular tie from point A by distance north delta n 53.2 and distance east delta E 156.13. So by definition, latitude is the north-south rectangular component of a line, delta n. To differentiate direction, north is considered positive plus and south is considered negative. Departure is the east-west rectangular component of a line delta E. To differentiate direction, east is considered positive and west is considered negative. When working with azimuth, the plus-minus designation of the latitude and departure is given directly by the appropriate trigonometric function. So latitude equal distance s multiply cosinus bearing, or latitude delta n distance s multiply cosinus azimuth. Or departure delta E equal distance s multiply sinus bearing. Departure delta E distance s na sinus azimuth. So latitude lets and departure depths, you can say lets and depths, can be used to compute the precision of a traverse survey by noting the plus-minus closure of both latitude and departure. If the survey has been perfectly measured, angles and distances, the plus latitude will equal the minus latitude and the plus departure will equal the minus departure. This figure shows that the survey has been analyzed in a clockwise manner. All algebraic signs and letter pairs are simply reversed for a counterclockwise approach. Latitude D E E A and A B are all positive and should precisely equal. If the survey measurements were perfect, the latitude of BC and CD, which are negative, departure AB and BC are positive and ideally should equal the departure CD and DE and EA, which are negative. In practice, however, random errors in each of measurements of distance and angle will result in residual errors of latitude and departure, such that the beginning point and the ending point of the traverse do not perfectly coincide. These errors of closure will be computed compared to the minimum allowable precision ratio for the type of survey being performed, and mathematically eliminated if the error of closure falls within the acceptable range. So, when bearing are used, the algebraic signs of the latitude and departure and depth are assigned according to the north, south, and east-west direction of the bearing. When azimuths are used, the algebraic signs of the latitude and departure are given directly by the calculator or computer according to the trigonometric convention illustrated here. So, latitude S is plus, cosinus alpha is plus, departure is plus, sinus alpha is plus for northeast quadrant. For southeast quadrant, latitude is minus, cosinus E alpha is minus, departure is plus, and sinus alpha is plus. Here, latitude is minus, cosinus minus, departure is minus, sinus is minus. So this is algebraic signs of latitude and departure by trigonometric functions, where alpha is the azimuth. Example: computation of latitude and departure to determine the error of closure and the precision ratio of the traverse survey. About survey data shown on this figure and used for this illustrative example. Following are all the steps required to adjust the field data and perform the necessary computations. So, solution. Balance the angle. See table and the arbitrarily balanced angle are used here. A B, C, etc. Then step 2. Compute the bearing or azimuth. So for traverse, we can find a bearing computation. So for AE, azimuth will be 172. 172. And for AE is identical to direction to the bearing of 7 south 7 degrees 21 east. And bearing for side AE is 7 degrees, so 7 degrees E. To compute the bearing of side AB, the two sides AB and AE are drawn together with a meridian through a point A. Interior angle of A will be a 101 degrees. This is the interior angle A. So what is the bearing in AB? Here it's apparent that the required bearing angle AB plus interior angle A plus bearing angle AE total 180. That is the bearing of AB will be 179 degrees minus this one. And plus this one. To compute the bearing of the next side BC, the line BA and BC are drawn together with the meridian through point B. Once again, the known data are placed on the sketch and a question mark is placed in the position of the required bearing angle for side BC. In step 1, the bearing of AB was computed. 171 degrees. When this information is to be shown on the sketch 2, yes, it's obvious that something must be done to make this data comply with the new location. With the meridian through point B, the line being considered is BE, not AB, BE. And the bearing becomes 71. So, bearing angle BC equal the interior angle B minus the bearing angle AB and equal 31 degrees. About azimuths. Azimuths AB equal the given azimuths AE minus the interior angle A. Step 2, BC. Here azimuth AB plus 180 will be azimuth BA, and then azimuth BA minus interior angle B will be azimuth BC, etc. All this information you can put in this table, and this is a typical format for a closed traverse computation. Here bearing azimuth and then latitude fail to close by 0.13 minutes, and that the departure failed to closer by 0.11. Compute the linear error of closure. The linear error of closure is the net accumulation of the random error associated with the traverse measurements. Closure error, you can see here. If the computation had started at any other station, the idential error of closure would have shown up at the station. So the perimeter and this is a E from error from the table. Precision ratio will be this divided by perimeter. So line A1A in figure is graphical representation of the linear error, and the length of this line is the square root of the sums of the squared of the C latitude and C departure. C latitude and C departure. We have a distance, this distance, and after that step 5. Where is step 5? Okay. So step 5, compute the precision ratio of the survey. So precision ratio is the linear error divided by traverse perimeter. And this resultant friction is always expressed with the numeration of 1 and with the denominator rounded to the closest 100 units. So this is a precision ratio. So I hope that you understand this topic, and by